Hi, my name is Bob Hanrahan, Field Application Engineer at Texas Instruments. Today, I'll be demonstrating TI's latest WebBench Power Designer, which can be found at webbench.ti.com/power-designer. WebBench Power Designer is a free, comprehensive online design tool used to accurately design DC to DC, AC to DC, isolated and non-isolated power supplies. By the time you finish watching this short video, you'll be comfortable creating a full end-to-end power supply design and exporting that design to your favorite CAD environment. WebBench has a brand new user interface for finding the best parts, which I find valuable in itself, but it also creates a reliable schematic and a bill of material, or BOM. It has simulation capability and also provides multiple ways to collaborate and share your design with others. Now, WebBench is applicable to all levels, from novices to those very experienced designers. It provides simplicity, yet many advanced features, many of which are now found in pull-down menus, some of which we'll show you today. The back end of the tool uses complex analytical equations to design and then analyze the performance of the power supply, yet the tool provides an optional SPICE-based simulator so you can see waveforms that you'd expect to see in the real world. But WebBench is not a full-blown simulator. For that, you could use TINA TI simulation tool, which is available online free of charge. What WebBench does provide is a reliable power design in the matter of a few minutes. A simulator simply can't do that. But in any case, all designs must be bench tested. All designs vary by layout. All PC boards are different. So you must test it to ensure the design operates as expected. And you can find my 4-part series on testing power supplies on the TI channel on YouTube or on our website, ti.com. So now let's go through a full WebBench design, and then at the end I'll demonstrate and validate that design on the bench right behind me. And then we'll compare the results and see how they match up. So let's say your boss asks you to design a battery-based power supply, but it needs to support multiple batteries. Let's say a 12-volt, 24-volt, and a 48-volt battery. And also wants to support a USB source, a 5-volt input. It must be small and also inexpensive. So you think to yourself, I don't provide some margins, so I'll design for down to 4.5 volts and up to 49 volts. Sounds like a pretty tall task for a single IC. You're thinking it might require a flyback design or maybe a multi-stage design. So let's see what WebBench comes up with. Let's put the numbers in. We start from the WebBench Power Designer landing page. We click on Start Design right under the DC to DC selection. Enter our input voltage, and as mentioned earlier, we decided on 4.5 to 49 volts on the input, 3.3 volts, and 3.5 amps on the output. Now, you'll notice 2 pull-downs, one under input, one under output, for optional settings such as an EMI filter on the input, and we provide the ability to set a maximum output ripple and other options on the output. Now, WebBench also provides the ability to select 4 different optimization settings. Now, this actually will adjust the coefficients of the algorithms such that you end up with a low-cost design, a high-efficiency design, or a design with a small footprint. Or, as often is the case, you're looking for a balance of all 3, so we'll use that today. Now, here another pull-down menu for optional settings, such as you can set your ambient temperature. I like using 50 degrees C. And here's a new one. We give you the ability to select a minimum component size. So if you don't want to work below 0603, or I sure don't want to go below 0402s, can barely see them and sure can't rework them, you have that ability. You can select to only use parts that provide an external sink and other options. And I urge you to look at the options and work with them. We just simply won't have time today. And at this point, click View Designs. So now we have a totally new way of picking the best part for the design. In less than a minute, the tool just went through thousands of calculations and sorted through hundreds of designs. In this case, it found 21 designs that match your criteria. I spend a lot of time on this page just studying the designs. Now, other than the card view that we see here, on the top right, you also have a table view. More traditional, here you can also sort on designs by just clicking on each of the columns. You have the BOM area or cost. We'll go back to the card view. It has a couple of features that aren't available on the table view. So here's a schematic. Again, it's at a high level you can get a feel for how many components, but by scrolling on any one of these cards, you can see the actual BOM, the component sizes, and that's a great way to just compare relative one design to the other. If you scroll to the right one more time, you have the efficiency graph for each of the designs available for quick view. In this case, we show you the graph overload from minimum to maximum, and at minimum and maximum voltage, and the center point. So below the design, you'll see some calculated numbers giving you the BOM count, the BOM area. And by the way, the BOM area is not only each package size added, but also we provide area around the package for routing. So that's a realistic number of what you'll be utilizing on a PC board layout. We also give you IC cost, as well as the BOM cost. That's the full BOM cost. We go out on the web to distribution, and we get the 1K pricing in real time. So that's a real good feel for again, 1K volume price. You'll notice the compare capability here. You can compare designs. We'll pick a few. Let's go down and take 3 of them. You have a compare pop-up shown at the bottom. We click compare. And here in a tabular format, again, you can compare one design to another. On the left side, more options where you can use these sliders to filter the designs down to just a few that meet your needs. And at the very bottom, we have the ability to select ICs that have certain features. As an example, frequency synchronization. If you select that, it will filter out all the parts that don't have that capability. Now, we won't have time to go through every one of these today, but I really do urge you to look at all the pull-down menus and try them. You'll find that the tool has quite a few functions that the advanced user will find valuable. So you can run with this design as is. Once you find the one you want, let's go with the 76003. It has a good efficiency, very small, has a built-in pass device, so as you could see compared to the one next to it, it's much smaller, and it's not a very high price. So at this point, and by the way, you could just run with the design as is and export, but a lot of people like to customize it further. Totally optional. But we are going to click Customize. So from the Customize page, we have 3 different tabs: Schematic, PCB Layout, and Bill of Materials. And below all 3 tabs, I'm going to scroll down, you'll notice Calculated Values. Now, we give you 4 different categories of values that you can observe and study, or the ability, if you click All, we give you all of the calculated values, both input and output. Now, these calculations are determined by an operating point that's shown at the top. In this case, it's the worst case voltage, input voltage of 49 volts, and output current 3.5 amps. You have the ability with the slider to move that, or you could type in a value. Also, you'll notice another tab where you could observe charts for the design. In this case, duty cycle, efficiency, and the actual Bode plot, loop response, is the default, though we provide up to a dozen, actually I think it's over a dozen at this point, other graphs that you can choose and display. Now, I like working at the schematic, on the schematic page, because you have the ability to change any component. As an example, here's the inductor, one of the larger components in your design. You can look at the component that was chosen, and you have the ability to click on Choose Alternate to bring up other options that fall within a selection range. You can sort on package size, on price, and make changes at that point. As an example, let's say you have an output capacitor in stock that you want to use. Well, the tool chose to use 200 microfarad caps, so I'm going to click Choose Alternate. Now notice at the top there's a range that the tool chose to stay within. You can go outside of that range by simply clicking Edit. And to get to the 47 microfarad, we will need to change that to 75 microfarad. So we'll do that for the lower limit. And it's a 10 volt component, so we'll click on voltage, go down to the 10 volt parts. And we see here two 47 microfarad muriatic caps. And that happens to be the capacitor you have in stock. By the way, if one of these changes pushes you outside of a safety margin for your stability, phase margin, gain margin, we'll give you a warning at this point. On the left side of the screen, you'll notice the ability to set your operating frequency, the switching frequency, if it's available on the component, the soft start cap, and other options. The PC board layout, what we do here is we show you our evaluation board with your actual components placed. And then the other tab is the bill of materials. A lot of people like working with the bill of material view. You have a lot of the same functions, the ability to select different parts, the ability to sort on size or cost. So at some point, it's time to move on. Now, again, you can move right to export and share your design as is, or you have the ability to use our optional SPICE-based simulator. So let's do that. Let's run simulation. So we click Simulate. And you'll notice 4 different simulation modes. We can run a full Bode plot to check stability. You can run loads transient simulation, input simulation, or in this case, we're not going to have time to run all 4, so we'll run a steady state simulation. By the way, we have a full training video on this simulation tool that's available on the TI website. So we'll start the design. We'll be using the output of this simulation to compare the output ripple to the actual bench measurement ripple we'll do over here to the right. Also, we'll compare it to the calculated ripple that we looked at earlier, which is in the operating values, and see how they all match up. So the tool draws the output waveform, as you can see on the right side. You can zoom in to the waveform by selecting a region. And if you scroll down below the waveform, the tool measures the output peak-to-peak ripple voltage. As you can see, it's a very impressive 3.44 millivolts, which, by the way, that is without any other noise contribution other than the output capacitor, ESR and capacitor value taken into consideration. So there will be more ripple when you look at this on the scope. Also, it gives you the frequency, 496 kilohertz, which is very close to the 500 kilohertz that we designed for. You do have the ability to display markers, so you can make spot measurements, and you could overlay other waveforms as well. So from this point, you can still go back to customize, make more modifications, resimulate, but at some point, we're done with the design, it's time to move to export. So we click on the export button. Now, I'll bring your attention to a few handy icons on the top right. We'll start with this share button. Now, this gives you the ability to directly email to peers. You can type in multiple emails with a note or create a public link. By clicking on Get Link in the lower left, you just sent yourself an email with a public link. You have a link shown here that you can just copy and paste, or we provide an icon to the lower right which copied it directly over to your clipboard. We also have an icon to download the datasheet. You can order the evaluation board so you can quickly try out your design right from the TI Store website, and an icon for the landing page for the part being utilized. Now I want to bring your attention to the lower left side of the screen. Here's where we create a report. By clicking on Print Report, you get a report with the full schematic, bill of materials, all of the graphs for your design. Real handy tool. You could bring it to your design review. It ends up answering a lot of questions that might arise. Obviously, you can still print the PDF, save it to your drive, and utilize it later. Now, on the top left is our ability to export a design to one of 5 popular CAD tools. Now, I happen to use Altium Designer, so simply click Export Design, and within a minute or so, we'll download a zipped file which will include both the PC board file as well as the schematic file. What you do is simply unzip the files, put them in the appropriate folder, project folder that you may have created, and that's a real good head start on your design. You can copy and paste it within the tool. So before I started, I took the opportunity of launching Altium, and here you can see the PC board file, and there's the schematic for the design that we just completed. So with that, let's come over to the bench and make some measurements. We'll be making 2 different measurements, efficiency and output ripple. For the efficiency, we'll measure over full load current, draw some graphs with Excel, and then compare those to the output of WebBench. And then we'll do the same for ripple. Now, for the equipment, we have a power supply on the input and a load box, dynamic load, on the output. 4 different voltmeters that we'll use for measuring voltage on the input, current on the input. We'll do that by, I've inserted a shunt resistor on the input and output, 0.1 ohm. And then over here we have our output voltage and our output current. So we'll turn on the input voltage. We'll start off with a 48 volt measurement at about 3 amps. So we set the input voltage to 48 volts, but we don't use the meter on the power supply. We come down to the meter that's connected directly to the input to the LM76003 board. We bring it up as close as possible to 48. There we go. We then move over to the load side where we set the load current, which again is shown down the lower right, to 3 amps. That's pretty close. That's good. And now we only need to take 2 measurements. So what I use is Excel. I prepared a spreadsheet with 3 input voltages, 5, 24, and 48, and 6 different output current measurements that we'll make. And I'll start with this measurement, which is 48 volts at 3 amps. And we see on the bottom left, 0.244 amps. And the top right measurement, 3.331. And you'll notice it draws a point to start a graph. Now, before we started the video, I took the liberty of capturing all the data. So I'll show that to you now. So here you can see the Excel spreadsheet filled in and the 3 graphs. On the left side of the screen now is the output from WebBench Power Designer. And as you can see, they look very similar. The x-axis is the same, the y-axis is a little bit different. And you can see that they're off slightly by about 2 to 3%, where the WebBench is showing an efficiency a little lower than the actual. And that is based on calculations that we use in WebBench. Rather it be a little better than what to expect. Now let's make our output noise measurement. Now for output noise, I always recommend taking off any unnecessary probes. So I'll pull off the voltage probes. Okay, we'll turn off channel 2 and we'll use channel 1 for this measurement. We open up the menu for channel 1, verify that it's AC coupled, and the vertical scale is set at the lowest level, 10 millivolts per division in this case. Today we'll be using the tip and barrel method, where we touch the tip to the output voltage and the ring to the ground. Now again, for proper probing technique, I suggest you go to the videos that we spoke about earlier that show how to make these very high accuracy measurements. And actually for the highest accuracy, I would use an active probe, not necessarily a passive probe, but this will be good enough for demonstration purposes. So we come in for the tip and barrel, we apply the tip to the output voltage and the ring to the ground lug and capture the scope shot. We'll try to get a good connection. Again, it's not a perfect connection, but it gives you the idea. 10 millivolts per division. It's a little higher than I measured just a moment ago. But what I did, again, just to save us time, is I captured a waveform. And as you'll see on the graph, I have it up on the screen, the LaCroix scope shot on the left, which showed about 5.5 to 6 millivolt peak to peak. On the top right, you can see that we have calculated 3.56 millivolts peak to peak. That's using the WebBench calculator. The WebBench SPICE simulator came up with 3.4. Again, 2 different engines, a little bit of difference in results, but fairly close. And as I said, when you're measuring noise at these low levels, you can expect it to actually be, show a little more than it really is in reality. So there you have it. We calculated and optimized a best-in-class power supply design in the matter of minutes. And the actual design performed close to what was expected by WebBench Power Designer. Think about how much time this can save you the next time you're asked to quickly design a power supply. Now, take what you've learned, go test drive the all-new WebBench Power Designer. Thanks for watching.